2, 3, 1, 2, 3. OK. All right, good morning. Okay, we'll start. So before the lecture, so please reminded that the second project is due by 10 days more or less, December 8, if I'm not mistaken. So Arnaud will be available to answer all your questions if you have any during next week. But we will not answer questions during the last weekend. So please do not send your, I mean, you can, but we will not answer. So if you have questions, please do so during the week. There are open office hours on Wednesday during lunchtime. So if you don't need to to send an email to Arnaud, you can just go to his office if you have any questions, okay? Also, regarding how we will evaluate this second project, will not be as strict as in the first project, at least regarding the performance, which I agree, maybe the evaluation criteria for the first project were a bit vague regarding at least our expectations. But you will not have something like this for the second project. Correctness will be the primary objective for us. Of course, your agent should not take minutes to decide on every move. But if you keep that within 1 second, more or less, it should be fine, okay? And what we more or less expect, so I don't know if many of you have already started or maybe already completed the second project, but so there are 2 parts in the project. You first have to estimate the positions of the ghost using a base filter. And then once you have this belief, you need to use it to decide on which action the Pacman agent should do, okay? So this strategy that we expect, I mean, there are several ways to use this belief, but one thing that you could do is to find, for example, the most likely position of the ghost under your belief, and then to determine the path between Pacman or the shortest path between Pacman and that position, and then to take the first action towards towards the ghost, okay? If you do that, everything should be fine with your project. Okay, do you have questions about this? Okay. Then today will be the last theoretical lectures. So we'll talk about reinforcement learning. We'll be more or less merging everything we have covered so far into one and single and actually very short algorithm. And you will see that with this algorithm, we'll be able to solve any kind of problem. Okay? So the main question for today will be how to make decisions under uncertainty. This is something we have already covered last week when we talked about MDPs, Markov decision processes. But the new twist is that today we'll not know the environment in advance. Okay, so we'll not have a direct access specifically to the transition model and to the reward function. Okay, we'll be able to interact and to observe the environment, and so to observe realizations of the reward functions or of the transition model, but will not be able to simulate them. Okay? So the lecture will be in 2 parts. We'll have first a passive reinforcement learning in which the agent will have a policy and we'll just try to evaluate that policy. And then second, once we know how we can evaluate a policy in the reinforcement learning setting, then we'll try to improve it. And that will be the second part about active reinforcement learning. Okay, so just to set things straight once again. So last week we covered Markov decision processes, MDP, and we were assuming that we had access, we knew this MDP. Okay? And when you know the MDP, then there are several things you may be interested in. So, for example, to compute the value of states or to compute a policy. The Q function is something we'll talk about today. We've only covered V and pi. And how can we compute the optimal policy, pi star, or the value of the states under the optimal policy, V star? We can do so using value iteration or policy iteration, as we have seen last week. We have also seen how to evaluate the quality of a fixed policy using policy evaluation. Okay? Today, we'll assume that the MDP is unknown, and we'll have two ways to solve this problem. One, which is model-based. We'll try to explicitly build a model, for example, of the transitions or a model of the rewards. And once we have this model, then we will solve as if we were under a regular MDP. Okay? But using our approximations instead. And then the second part, or the second approach, is the model-free approach, in which we'll never explicitly build the transition model or the reward function, but we'll directly try to compute the v-value or the pi policy. Okay? And you will see that there is actually a way to learn these functions without ever having to instantiate, for example, a transition model or a reward function, which we don't have anyway. Okay? All right, so I will start with a short recap just to refresh you about what we covered last week, because we'll just be building upon that framework. So we have defined Markov decision processes, MDPs, as a tuple of 4 components, a set of states. So all the possible states that the agents can be in, a set of actions, which can be conditioned or restricted depending on the states S at which we are. Then we have also said that as part of the MDP, we have a stationary transition model, which in our case is modeled as a conditional distribution over the next states, given a current state and given an action. Okay? Where, of course, S and S prime are members of the set of states, and A is part of the set of actions. Okay? And then finally, we have also said that an MDP is made of a reward function, okay, which is, in our case, a function which associates a scalar value to any state S. Okay? Like a score, basically. And this reward can be positive or negative, depending on the environment, depending on the states, and so on. You may also include, as part of the MDP, a discount factor, gamma, which is a value between 0 and 1. Okay? Now, in an MDP, we were assuming that we have an agent which has to take actions one after the other. So we have discretized time into discrete time step, and at every time step, the agent has to decide on an action. Okay? So the agent knows its current state S. Then from this state S, decide on some next action A. Then this will result in a new state, S prime. Okay? This next state is not necessarily deterministic. Okay? It can be a random realization from the transition model. And then once the agent that has transitioned to this next state, it knows this next state and also knows the rewards associated to these next states. Okay? Or in what we have assumed last week, instead we were saying that the agent does not receive the rewards directly, but has access to the reward function and can evaluate the reward function to any of the states S. Okay? Okay, so we have also said that these Markov decision processes, they can be generalized to continuous state action spaces. So when, for example, the set of states is described by variables that are continuous, or when the set of actions is described by variables that are continuous, then we would have infinitely many elements in these two sets. And so we can generalize MDPs to this setting. That's perfectly fine. However, none of the algorithms that we have seen together can be used in this context. Okay? This will be for later if you follow other classes. Also, if some of you read about reinforcement learning, for example, on the internet or in textbooks, you may find alternative formulations. And one of them, which is very common, is to define rewards not as just a function of states, the state at which you arrive, at which the agent arrives, but instead as a function of the starting state, the action, and the ending states. Okay, so as a function of a triple S, A, and S prime. Okay? And because of that, if you redefine the reward in this way, you have to redefine all the equations we have covered together, including the Bellman equation, everything. So this can be done. And of course, then the algorithm that we have seen also would need to be changed, but that's something you can do. So don't be surprised if you see this other convention when you read about reinforcement learning. What you should know, however, is that an MDP is formulated either under these assumptions or either using rewards as functions of this triple are more or less equivalent. Okay? Or one can be made equivalent to the other and vice versa. Okay? Okay, then next we have covered the Bellman equation. So we have said first that the value of a state for a policy pi was equal to the expected value of the sum of discounted reward that you obtain when you run the policy pi, okay, starting from S0 being equal to S. Okay? And we have also said that actually this long-term sum of discounted rewards can be written using the Bellman equation as the immediate reward that you get by reaching S plus the discounted value, the discounted value of the next state in expectation over the next states when you follow the optimal policy, which is the one which should maximize this expected V value. Okay? So it's the max okay, so at least for the optimal policy, you have that the V value is equal to the immediate reward plus the expected V value of the next state S prime. Okay, and you do that by just iterating over all possible next states, and you weight them by their probability, P of S prime given S and A. And then you assume that you follow the optimal policy, meaning that you would be picking the action for which this quantity is the largest. Okay, and then you discount by a factor of gamma. Okay? Next, we have covered from the Bellman equation the value iteration algorithm, which is an algorithm that we can use to compute the V values. And so the trick is just to instantiate a very big table V, okay, which is as big as the number of elements that we have in S. Okay? And then we bootstrap this V value with just random or arbitrary values. You can set them, for example, initially all to zeros. And then the trick is just to run a fixed point iteration algorithm where we'll be trying to solve this system of equations. Okay? So the Bellman equation is not actually one single equation. It's you have as many equations as you have states. So you have a system of equations. The only issue with the system of equations is that the equations are nonlinear because of the max operator. Okay, so you need numerical algorithms to solve it. One of them is just to run a fixed point iteration algorithm. And if you do that, you arrive to the value iteration algorithm. And so at every iteration of that algorithm, what you do is that you make your estimates of the v-value a bit more consistent with the Bellman equation by saying that the next iterate vi plus 1 is equal to the immediate reward plus the discounted maximum expected utility of the next state. And of course, you don't know the utility of the next state yet because that's what you want to estimate, but you can use your current estimate to improve it. Okay, then you repeat that until you converge. An alternative to this algorithm is the policy iteration algorithm, in which instead of iterating over the v-value, you're directly iterating over the policy functions. Okay, and so this algorithm works in 2 steps. First, you extract out the v-value associated to your current policy, not pi star, but pi I, okay, using policy evaluation. In policy evaluation, you use this equation, which relates the utility of each state to the current reward and the utility of the next state, assuming that you follow the policy pi I, not the optimal policy. And because you are not following the optimal policy, this max operator disappears, and you replace A by the output of the policy function. Okay? And then you fall back now to a system of linear equations, which are much simpler to solve, which you can from which you can then extract the v-values associated to the current policy, and then you improve the policy pi to pi I plus 1 by just using a one-step look ahead based on the current estimate. Okay? Questions on this? Okay, so this was a short 10-minute recap of the lecture of last week. Okay. Now, what we will do is that we will assume that basically this component, even though it's there, so this one, we know it's there. We know that we can, or we assume that we can formalize the environment as a MDP, but we'll not know this transition model. Okay? So that means everywhere where we had to compute this expected value of the v-value of the next state, where we were relying on the knowledge of this transition model, we will not be able to do that any longer because we can't evaluate it. We don't know it. And similarly for this function, the reward will still observe reward values, okay, but we'll not know how they've been computed. Okay, so that means we'll not be able to evaluate rewards on any state S. Okay, the only knowledge that we'll have will be for the rewards that we have observed by just interacting with the environment. Okay, so solving this problem is the goal of reinforcement learning. And to motivate that, I will start with 2 videos, 2 examples of this chicken. Okay, so let's see. What have you observed? What are the rewards?
The food.
The food?
I don't know how to put the click sound into a box. I know that this click sound comes, but maybe it's just to associate.
Yeah, it's just one. It's a signal that which is equivalent to a reward.
Okay.
So the food is the reward. How do you get more rewards? How do you get more food?
Pointing to the rose.
Yeah, to the pink circle. Yeah. So how do you believe the chicken solving this problem?
He randomly does an action, and for the actions which result in the higher reward, he repeats those actions.
Okay, so, and when it, okay, but how does he know about these actions? Or the outcome that will come with doing these actions?
It doesn't, no.
Yeah, it doesn't, of course, yeah. But eventually it seems that he knows what he should do, right?
But it knows that when it does the action point to the pin one, it's more likely to receive a reward than the other actions.
Uh-huh. How does he know that?
Trial and error. Maybe at the beginning, I don't know, it showed, try to just go around and at random moments, because he doesn't know, he became something to eat.
Okay, so let's watch it once again and then observe at least at the beginning of the episode. Yes?
Well, I think by training, because in the beginning it was one object, so 3 times. After the 3 times and getting the reward, she's training and recognizing this is the right one. So we added one, and she answered right. Then we added the third one.
Mm-hmm.
So and this is how it's going.
Yeah, but he could have gone for the others. He could have gone for the others too.
But it's like she marked it.
Yeah, but maybe if you go for the orange, you will get even more food. How do you know?
It's the habit. She gets a habit.
Okay?
Every time it acts on the pink circle, there's a click and a reward associated with it. And at some point, if repeated enough, it becomes an association. This action equals 1 food, and then trying something else could potentially lead to better, but the past history has proven that this action will always be associated.
Yeah. But let's observe if at some point the chicken tries to do something else than going for the pink one. He went for the blue and then there was no click. Okay, so at the very beginning, there is some explorations. Okay, it goes for the blue at least once, but then there is nothing, and then eventually just exploit the fact that okay, if you go for pink, you get a reward, and that's it. Okay, and then it always goes for that. So let's now look at another task. Okay, what happened? How do you get the food? The chicken figured it out, so I suppose you did too. How do you get the food? Yeah.
Around the cone.
Okay, yes. And what have you observed?
Actually, it doesn't really know what to do.
Yes.
It gets food, but doesn't really know why.
Yeah.
So it tries something.
Yes.
Goes around the cone, ends up getting more food, so still isn't sure, tries again.
Mm-hmm.
And again, it seems it's someone figured it out. So not completely.
What about the third attempt, when it does a circle but not around the cone? Then he noticed that in this case it does not get any food, and then figure it out, and then just go around the cone and eventually get the foods. Okay, so actually this is reinforcement learning. Okay? There is an MDP. We've not explained the MDP to the chicken. I mean, you could try, but don't think that will be very useful. Okay? And instead, what you have is an agent in an environment. So it can take any set of states, has to decide some actions. There is some transition which happens, okay? And you may have rewards depending on what you've done. Okay. And you could say, okay, if I knew all these elements, well, I know my Bellman equation, I can just solve it. But of course, the chicken does not use that. Or maybe, I don't know. So how would you solve this problem? That's what we'll try to answer. But what is really insightful from these two videos is that actually it's not really just only planning. I mean, eventually it's planning, and it's really obvious that it's planning at the end of the first video, where you just keep exploiting this knowledge, go for the ping, go for the ping. Then it's just about going there. So this is planning. But before that, you have also to discover the environment. You have to learn about the environment. And this is really reinforcement learning. Okay, you have to act to figure out the environment. So in this case, there was an MDP, but the chicken couldn't solve it with by just solving the Bellman equations. And instead, the chicken needed to act to actually figure out the dynamics. To figure out the dynamics, so what are the transitions doing, and also how rewarding are each state. Okay? There are also very important ideas that you can observe in these two videos. The first one is the concept of exploration. Okay? So when you don't know in advance what will be the outcome of your actions, you have to act to collect information and then to learn what will be the consequences of these actions, both in terms of the next states and the rewards. But then eventually, once you know, you should exploit your knowledge. Okay? So this is the concept of exploitation. Eventually, you should use what you know. Okay? There is also the concept of regret, which is even if you learn intelligently by exploring actions for which you don't know the outcome yet, you will make mistakes. Okay? That's the case, for example, for the second video. In the third attempt, it goes in circle, but not around the cone. Okay, so it's making a mistake. Okay? Then there is the idea of sampling. Because the environment can be stochastic, you have to try things repeatedly. Okay? To actually really figure out if, at least in expectation, these states are useful. And also it can be difficult. And learning, in this case, would be much harder than just solving a known MDP. Okay? Because we'll be solving two problems at once. Learning, there will be a machine learning problem in which we'll have to estimate all these components, and then an optimization problem in which we'll have to figure out the optimal policy. Okay. So formally, a reinforcement learning problem can be summarized again as a Markov decision process with the same component, a set of states, a set of actions, a stationary transition model, a reward function. So everything is the same as before. And the goal will be the same. We'll be trying to identify an optimal policy pi star, which given a state tell you what to do. And if you are following this policy, you will be maximizing this expected sum of discounted rewards. Okay? But now there is a new twist, which is that, okay, even though the agent knows the current state it is in, it does not know how this state has been obtained. Okay? So the agent will get access to the next state S prime, but only to realizations of this transition model by taking actions through the environment. But it will not know about the transition model itself. Okay? So it's as if you knew that there was some distribution. I don't tell you which, but you can ask me to produce realization random samples. And then you have to figure out from which distribution I'm sampling. And the same goes for the rewards. You only observe the reward values, but you don't know the function itself. So you can't evaluate the reward function since you don't know it. Okay? But you may assume that there is such a function which associates a reward value to a state S. Okay? So the assumptions are the same, except that now some of these components, the rewards in the transition models, are unknown. They are still there, but unknown to the agent. Okay, so now that we have formalized the problem, we'll try to solve it. And the first problem we'll consider is the case of passive reinforcement learning, in which we'll assume that the agent policy's pi is fixed. Okay, so we'll not try to improve it yet. And the goal will be, so pi is fixed. And what we want to compute is v pi. Okay, the value of the states if we were to following this policy. Which means that if we follow the policy also, we'll not have the opportunity to make random moves. Okay? We just have to follow the policy. And we'll try to evaluate its quality. Okay, so as an example, this is something I will reuse today a few times. Let's assume that we have a very simplified environment, a five-cell grid world, A, B, C, D, and E. We assume that B and E are initial states, that A and D are terminal states, okay, and that the policy of the agent is fixed. And then we just let the agent runs through this environment. So we could have a first episode where we start in B, we collect a reward of -1, then we follow the policy, which tell us to go east, and we arrive to the next state, S prime being equal to C. Okay, so we make this transition from B to C. Okay, then we repeat. In C, we obtain a reward of -1. The policy in this new state tells us to go east, and we arrive to the next state, D. And finally, at D, we collect a reward of +10. There is no more action to do, so because that's a terminal state, and there is no next state because that's a terminal state. Okay? So we'll have trajectories of state actions. We can repeat that for as many trials as we want. So we could have a second trial in which we start in B, collect the same -1 reward, still decide to go east because we have a deterministic policy, and then we arrive to C. In C, we collect -1, we decide to go east, we arrive to D, and then at D, we collect a reward of +10. Okay? We could have also started either in the other initial state E instead of B. In this case, we collect a reward of -1. The policy tells us to go up, to go north. we arrive to C, and then at C, we collect the same reward as before, east. We decide to go east, we arrive to D, and then at D we collect plus 10, and that's it. And then maybe we would have a fourth trial, at which we would still start from the E state, decide to go up, we arrive to C, collect -1 reward, decide to go east, but instead of arriving to D as before for the 3 other cases, we arrive to A. Okay? And at A, we collect a -10 reward, and that's a terminal state. Okay? So in this case, what you see is that when we are at C, if we go east, okay, because of the transition model, this one, which is stochastic, we noticed at least from these 4 trials, we have 2 possible outcomes that we've seen at least. We may arrive to D or to A. Okay, so if you are in this kind of scenario where you have a fixed policy, you can play the policy within the environment to build these trajectories. How would you solve then the passive reinforcement learning problem, in which you want to estimate the v-value for pi? So, if you don't remember the v-value for pi at S, okay, you can use the Bellman equation, but for a fixed policy, and that's the immediate reward plus the discounted expected value of the next state when you keep following the same policy. And sorry, instead of A, here you have pi S. So how can we evaluate the v-values for pi? Can we use maybe these trajectories to do something? Yeah.
Maybe on one trajectory, you can evaluate a sample of that v-value, which is random. No, it's not random. Sorry. Maybe you can, on all the paths, take the average of the v-value. So if, for example, you want the v-value at C, you would take R of C on that trial plus the gamma times V, which is the reward at D. And so if you do that and take the average over all the trials, you will get maybe the right answer.
Yeah. So here really what we need to do is, so that can be rewritten as an expectation over the transition of the v-value of the next states. Okay? And how do you estimate an expectation? Yeah, you can use as an estimator of the expectation just a Monte Carlo average. You do an empirical mean, so you sample finite number of times from this transition model, and then with these realizations, with these samples, then you compute the empirical mean of this. Okay, that will give you an estimate of the expectation. Okay, that's exactly what we can do. But that will be the model-free approach. So that's something I will see actually in not the next slides, but the ones after. Could we do something else? So we could do this and directly estimate the v-value. That would be fine. So the two unknowns are R and P. Can we estimate these two components from the trajectories? How?
R, it's not random.
It's not random in our case.
Look at one.
Yeah, so that's correct. So since we assume in our formalism that R is not random, as soon as we observe the reward value for a state, we know the value of R for S. That's good. What about P? Yeah. Okay, so if I try 4 times, what can you estimate about P? For example, how would you, what would be from these trials P of S prime given S being equal to C and action being equal to east? So okay, sorry. For A, and you said it would be equal to? Sorry, D. And for this one? 3/4. And for this one? Yeah. Okay, so you can use your observations to build empirical estimates of the probability of the next states. Okay, so in this case, we had 4 transitions starting in C and then going east. Out of the 4, for 3 of them, we arrive to D, and for the remaining one, we arrive to A instead. Okay, so that's why in this case we would be computing 1/4 for the estimated probability of arriving to A and 3/4 for arriving to D. Okay, so if we do this, we have something which is called model-based estimation, in which we'll build models models of the unknown transition models and of the unknown reward functions. So we'll build a P hat. So the hat denotes the fact that this is an approximation of the actual thing. Okay, and we'll do so using the empirical samples, so the transitions that we've observed. We could also have used machine learning to estimate these distributions, because, I mean, this is just an input to output problem. This is a supervised learning problem for which we have a data set, okay, that we can extract out from the trials, the trajectories that we have. Okay, so you can also use neural networks, for example, to build these approximations of the transition model. And for the reward function, then we'll just use the values that we have discovered for each S. Okay? And once we have estimated these 2 components, then we can plug them. Instead of R, we'll be using R hat, and instead of P, we'll be using P hat, okay, or 2 approximations. And then under these approximations, now we are back to a system of linear equations from which we can extract out the V values. Okay? So you just approximate your MDP, and then you use, in this case, policy evaluation on your approximated MDP, and you obtain the v-values. Questions on this so far? Okay. Yeah, this is an example, but actually this is something we've already started discussing. So from these 4 trajectories, we can learn transitions under the transition model, from which, for example, the estimated probability of arriving to C starting from B and then going east would be equal to 1. Would be equal to 1, because in the 2 transitions where we start in B, okay, we always arrive to C. Okay, so this is 2 over 2 equal 1. This one we've discussed, and we could do so for all the transitions, all the pairs of S prime and the triples actually, S action and S prime that we have observed. Okay, and for the reward, in this case, we've observed the negative reward of -1 for B and C, a positive +10 reward for D, and so on and so forth. Okay? So that's something that we can do, which will work to some extent. The issue with that is that the agents may not necessarily fully explore the entire state action space. Okay, and so that means maybe there are parts of the transition models, or maybe there are parts of the state space at which the reward function has never been evaluated. Okay, so that's a big issue with this algorithm. But if you use, for example, instead of machine learning approach, you will always have answers for everything. Even if these answers are wrong, at least you will be able to use it. But if you just maintain a table to compute the probabilities or the rewards, then there will be holes, missing values in your tables, unless you have explored everything. Okay, the second approach is model-free estimation. So where the question is, can we learn the v-values without explicitly modeling the environment, so without explicitly instantiating approximation of the reward or the transition model? Okay, the answer is yes, and that was your first actually approach, and it's called Monte Carlo evaluation or direct utility estimation. Okay, since we have trajectories, we have actually realizations out of this expectation. Okay, so the v-value is the sum of the discounted rewards, but in expectations. So that means when you start from some state S0, you will get a random trajectory from which you can compute this sum of discounted rewards. Okay, and that's exactly the trajectory that we collect. So that means now we can just, again, estimate this expectation from the samples that we have observed. Okay? So the utility v pi of s is the expected total reward from the state onward, okay, as we know. And what is interesting is that each trial provides a sample of this quantity. Okay, if you sum all the discounted rewards, you will get a sample of the inner part of the expectation. Therefore, at the end of each sequence, we can update a sample average v at pi of s by computing the observed reward to go for each state. Okay, so the idea is to so we have B, for example, C, and then E, A, no, it was T, E. So we could have a first trajectory where we observe -1, -1, plus 10. Okay, And from this trajectory, we can compute the reward to go starting in B and then up to a terminal state, up to the end of the trajectory. Okay, so the value that you observe from the reward to go is -1 plus gamma times 1 minus 1 plus gamma square times 10. Okay, and then that's value. If gamma is, let's say, equal to 1, we observe a value of plus 8. Okay, but from that same trajectory, we have also the reward to go starting from C. Okay, where the reward to go starting from C is equal to -1 plus gamma times 10, so plus 9. And finally, from that same trajectory again, we can start in D. We observe a reward to go of plus 10, and then no more states afterwards. Okay? So from the trajectory, you can extract basically all the suffixes of the trajectories, and then from these suffixes, use them as samples to estimate this expectation. Okay, questions on this? The issue with that would be this problem. Okay, so if we run direct utility estimation, so the values that we would obtain would be these ones. So for example, for B, we would have plus 8, y plus 8, because we observe two sequence where there is B at some point, up to a terminal state. So in the first trajectory, we would have -1 plus 10 plus 8. And the second, we have -1 plus 10 plus 8. Then you take the empirical average of plus 8 and plus 8. That's 8. Okay. For C, we can use these 4 suffixes. And so we take the empirical average of -1 plus 10 plus 9, -1 plus 10 plus 9, -1 plus 10 plus 9, -1 minus 10, so minus 11. So that's the empirical mean is 16 plus 4. Okay, you have plus 9, plus 9, plus 9, minus 11. You divide by 4 because you have 4 trajectories. And that's plus 4. For E, you would have -1 minus 1 plus 10 plus 8, -1 minus 1 minus 10, minus 12. Then you take the average of plus 8 and minus 12, and you would get minus 2. Okay? Now, the issue with this algorithm is that, okay, actually, from what we observe, it seems a bit strange that you associate with this algorithm distinct values for B and E. Because if under our policy, and that's the case, if we are in B, the only thing we can do is to go to C, and if we are in E, the only thing that we can do is to go to C as well. Okay, we have only one possible action. Okay, and that's the action taken by the policy. So if in these two distinct states we always reach the same next state C prime, how could it be that we associate two distinct values? So our estimates would tell us that B is more interesting than E. But that's not true. Okay, the issue with this algorithm is that basically direct utility estimation misses the fact that the state values, they are not independent. The value of a state depend, of course, on the immediate reward that you collect at the states, for sure, but also a state is interesting because it also connects to other interesting states. Okay, so the neighborhood of a state is also what makes a state interesting. Okay, and the neighborhood is taken into account in the actual V value. Okay, through the Bellman equation. Okay, so since the v-value obey the Melman equation for a fixed policy. Since we have that, it seems that we are missing a chance to learn about the actual v-value if you only look at the reward to go that we observe for a state without taking into account the reward to go values that we observe at the connecting states, at the neighboring states. Okay? Questions? Okay, let's take a 10-minute break then, and then we'll see how to fix this problem. Okay, we'll restart. Okay, so we were dealing with this problem of passive reinforcement learning, in which we have a fixed policy, and we just want to evaluate the v-values associated to this policy. But since we are in the reinforcement learning setting, we don't have directly access to the reward function, nor to the transition model. Okay, we only get to have observations or random realizations out of those. Okay, we have already outlined two strategies to solve this problem under these assumptions. The first one is the model-based approach, in which we are using the trajectories to build models of the reward and of the transition dynamics, using tables or using machine learning models. Then we were wondering if actually we need to approximate the MDP in the first place, if the only thing we care about is to estimate the v-value. The answer is no. We can directly estimate the v-values without directly instantiating or modeling the rewards or the transition models. And we have seen a first way to do that, which is direct utility estimation. We just use the trajectories to compute, to extract out reward to go values that you use to estimate this expectation. However, it comes with some issues. If you do direct utility estimation, you are missing it. So you are missing the fact that the v-values, they are related to one another. They are not independent. And because of that, this algorithm is very, very, very inefficient. Okay, you will need to collect many, many of these trajectories to do a good job at estimating the v-values. Okay, the alternative is to, instead of saying I will learn from trajectories once I've collected them, what we can do instead is to say I will learn from every transition. Okay? And so this is the concept which is used by temporal difference learning, which is the name of the algorithm that we'll see together. And so the idea is to maintain an estimate of the v-value, as before. Okay? But each time the agent experiences a transition, okay, each time we have a transition starting state, reward, action, next state, and actually we have a bit of knowledge that we can use to estimate the v-value. Okay? And so the idea is that, I will do it there because I will use it. So we are currently in a state S. Then the policy tells us to follow some action, pi S. And we arrive to a chance node over which we have no control anymore. Okay? From this chance node, we may arrive to this next state S prime. Okay? But so all these components together, they define this transition S A equal pi S. Oh, sorry. And the reward should be reward A pi S and then next. Okay? So the idea will be to use all these transitions, these tuples of 4 elements, to improve our estimates of the v-value. Okay. And so if we have an estimate of the v-value, a current estimate v pi s, okay, we can relate, or we can compute the difference between our current prediction and this quantity r plus gamma times the prediction for the next states. So what does that mean? It means that if we are currently in state S, the current estimate is to say that the value that we associate to this state S is V of S. Okay? But because of the Melman equation, we know also that this quantity should be related to the immediate reward that we have collected at S plus the discounted value that we have when we reach the next state S prime. Okay? So these two quantities should ideally be the same. Okay? But if we do observe that there is a difference between the two, it means that our estimates are inconsistent. Okay? And then the trick is just to say in temporal difference learning, you will minimize this inconsistency, you will minimize these so-called temporal difference errors. Okay? And you will do so by just doing a step of a gradient descent on the v-value to minimize the temporal difference error. And so you say that you will update the new value of v for s is its current value, okay, plus alpha, which is a learning rate, a small coefficient, times the temporal difference error. So, for example, if we have that the immediate reward plus the discounted value of the next state, so if this quantity, so if R plus so if we are in this setting, if our prediction is larger than the estimate, or if our prediction, this is our prediction, is lower than this value, it means that we are currently underestimating the v-value. Okay, so we should make this value v greater. Okay. So when that's the case, the difference will be positive, okay? And we'll just increment the v-value by this error times a small coefficient alpha. And on the other hand, if we have that our prediction is larger than what it should be, than this target, then it means that we are overestimating the v-value. Okay, we are overshooting. So in this case, we need to decrease the v-value. Okay, but if that's true, then now the temporal difference error will be a negative value. Okay, so in this case, the update will decrease the value of v. Okay, does that make sense to everyone? So you can also view that. You can view the temporal difference update as a single gradient descent step on the squared error between the target, what we would like to estimate, and our prediction Vs. And we'll see in a few slides that this is indeed the case. You can also view the update as an exponential moving average, where you can re-express the update to obtain the new iterate for the v-value, Vs, as the an exponential moving average. So you say that you forget about your current estimate by a small amount alpha. So you say that V So you have this term which accounts for 1 minus alpha, and then you add alpha plus the target value that you observe. Okay? This one you observe from the transition. Okay? From the transition, you have the reward, and you know that you reach the next state S prime. Okay? So intuitively, you can also understand this equation by just saying that you will make all the recent samples more important, okay, and you will progressively forget about the initial samples if you view that as an exponential moving average, which is fine because you know also that the distant values that you were considering for V were wrong because they were based, for example, on your initial guess and not on the transitions that you have observed. Make sense? Okay. So this is an example on the same grid world. So let's say we are in B, and then we have a single transition. So we are in B, we observe the reward -1, then we decide to go east, that's given by the police C, and we arrive to C. Okay? So you can use temporal difference learning to update the V value. Okay? In this case, the TD update, assuming a discount factor equal to 1 and the learning rate of 0.5. Okay? So in this case, the TD update would be an update about B. So the new iterate for VB would be the current value VB plus alpha times the temporal difference error, which is defined as the target, which is defined itself as the reward, so in this case, -1, plus gamma times the V value, or at least our current estimate of the V value for the next state as we experience from the transition, so for the next state C. Okay, that's the target, that's what we want to predict. And then we just compare that to our current estimate, VB. Then now we replaced all these symbols by their numerical values. If we say that, so the black values correspond to the current estimates of the V values for each state. So VB is equal to 0, learning rate is equal to 0.5, the reward RB is equal to -1, that's the one we have from the transition, gamma is equal to 1, VC is equal to 0, so 1 times 0, 0, minus the current estimate for B, which is 0, so -0. Okay? And that means that then after the update, the value of B would be -0.5. We can do the same for C, the second transition. So if we have the transition C, reward -1, action to go east, and then we arrive to D, then we have a similar TD update, where the new value for C is equal to its current value plus alpha times the temporal difference error, which is the reward plus the discounted value of the next state D minus the current estimate VC. Again, we replace all the symbols, and we have 0 plus 0.5 times -1, the reward, plus the current estimate for D. So in this case, assuming we had already this knowledge, or this estimate for D of +8 minus 0. Okay? And then the new value for VC would be equal to 3.5. Okay? So there is so what is interesting about this algorithm is that highly rewarding states will quickly propagate their values to their neighbors. So in this case, the value of 8 propagates its value to its predecessor C, okay? If we experience a transition going from C to D, okay? And if we experience one more transition from B to C, given these current values, then we would have that B would become even more accurate. Okay? And it would profit from the values that we have propagated upwards from D to C and now from C to B. Okay. What is also interesting is that now if we experience a transition going from E to C, we also directly profit from the knowledge that we have about C. Okay, so directly the value that we would get for E would be much more accurate than the kind of value or estimates that we had with direct utility estimation. Okay, because we'll profit from the fact that all these trajectories, they share suffixes, they have suffixes in common. And so if at some point we arrive to somewhere that we have already visited through another transition, then we will exploit this knowledge to more quickly propagate the values. Okay, but does it converge? So there is one thing that maybe you've noticed is that in the TD update, we only take into account the successor S prime that we have observed. But actually, in the actual Bellman equation, we have this transition model there. Okay, so in principle, we should have accounted for all possible next states. Okay, the target value R plus, so this one is not really our target. The real target should, because we don't know, in reality, we don't know about S prime. We don't know if we will always reach S prime. Okay, so the actual target should have been maybe this. Okay, which then we compare to this. Okay, but we don't have access to that quantity. Okay, but that's fine because what we are actually implicitly doing is doing a Monte Carlo estimate of this quantity. And so if you look at the average value of Vs, then this average value will actually converge to the correct value. Where I mean the correct value being this one. Okay? Also, what is important is that if we change alpha, the learning rate, from a fixed parameter to a function that decreases with the number of times we have visited the state, such that eventually we don't update the v-values anymore, okay, because alpha has shrunk to 0, then in this case, v will itself converge to the correct value. Okay? If we have a fixed positive learning rate and we keep doing these TD updates, of course, the v-values will keep changing. They will not converge. But their average value will converge. And the value themselves will converge if the learning rate eventually decreases to 0 as we have visited more and more the states. Okay? All right, so now we have a few algorithms that we can use to evaluate a fixed policy under the reinforcement learning setting without knowing P or R. Now, of course, what we want to do is to learn the optimal policy. Okay, so now we'll relax our assumptions. We'll say that the policy is not fixed anymore, and we want to improve it. Okay, and supposedly we want to find the optimal policy by star, or equivalently, we want to find the state values Vs, okay, which are associated also to the optimal policy. Which means that now the agents will have the opportunity to make choices if we want. Okay, since we are improving the policy, we are deciding what are the next actions. Okay, these actions, they are not imposed anymore. And this is where we'll use this trade-off of, on the one hand, exploring states which we don't know yet, and exploiting states for which we have a good understanding of their dynamics and of the rewards that are associated to them. Okay, so again, there will be two approaches, a model-based approach and a model-free approach. So in the model-based approach, so So in the model-based approach, if you remember, what we have done is that we let the policy run, we collect trajectories from which we estimate, we make a model of the reward and of the transition model. Then we solve to evaluate the policy, meaning to obtain the v-value associated to v. Okay? And we have seen that one yes. And then if we can do that, then we are just back to an MDP. Okay, we have an approximated MDP, and we know algorithms to solve MDPs. Okay, we can just, for example, use value iteration or policy iteration. Okay, but using or plugging inside the approximate model. If you do that, fortunately, nothing will work. So if you remember this problem from last week, if you have a random agent, let's say initially, from which, or not optimal agent initially, from which you estimate, from which you collect trajectories, and then from which you estimate reward and transitions, then you obtain an approximated MDP, which you solve to obtain the optimal policy. The optimal policy, in this case, would be this one, which is quite wrong. Okay, it's far from being optimal if our goal is to reach this highly rewarding cell, if you remember. And so that means that the agent that we would learn in this case would not be the optimal agent. Why is that? So basically what we are doing is that we start from some agent, which certainly is not optimal in the first place. Okay? So for example, let's take the case of a game, like the case of Pac-Man, which you know quite well now. Okay? And you start with an agent, which is not that good, okay? But which you can run, from which you can collect trajectories, and from these trajectories you can estimate a reward and a transition model. Now, given this reward and transition model, you instantiate a regular MDP, which you solve using value iteration or policy iteration. That gives you the optimal policy. Would you expect this policy to actually be optimal?
Yes.
Yes? Who else? Okay, let me rephrase, and then we will see if you change your opinion. Let's say I'm taking one of the projects for which you have obtained less than 10 out of 20. Okay? It's not optimal. Okay? You have certainly too many exponent nodes. Then you do this, you let it run, you extract trajectories, you learn a reward and a transition model, you do value iteration. Do you obtain the optimal agent now from this poor solution?
We only look at bad trajectories.
Exactly. Okay? So since the agent is not optimal, it will not explore the entire state space. And it's really, in this case, biasing the transition and the reward that you actually observe, and then on which you base your next algorithm to try to extract out the optimal policy. So this is exactly also what happens there. Okay, so the resulting policy, okay, could be better, and certainly would be better, but it's still greedy and suboptimal. Okay? And the reason is that the learned transition and reward models are not the same as the true transition model and the true reward function. Okay? Because we have learned them from a strongly biased samples of trajectories. Okay? And for this reason, what is optimal in the learned model can be suboptimal in the true environment. Okay, so how do we fix this then? Yeah.
We add some random moves to explore and fit the environment.
So to make it better, you make it worse by just saying that sometimes you will make random moves. And why?
Because that way you explore more paths and you have more information about what can give you a better result, more information about the environment and a better transition on estimation.
Yeah. So this simple trick is enough to fix it. If you say that you will keep, so maybe 1 every 10 moves you will make a random action, then because of this budget that you dedicate to these random actions, you know that eventually you will have explored the entire state space. Okay, from which then you will be able to collect, to learn proper models. So this is called the exploration mechanism. So as I said, the actions, they do more than provide rewards. They also contribute to learning the true environment. So of course, we should exploit to follow the actions that maximize the rewards. It would be quite inefficient, of course, on the other hand, to just learn from a random agent. Okay, it could work eventually, but would be certainly slower than starting from a better agent than a random agent. However, still we need to explore. We need to follow actions, random actions to explore and learn about the environment. Okay, because maybe there are parts of the environment which we have not seen yet or not enough, and from which we should learn. Okay, how to explore? So we know we have to explore, but how should we explore? So what you suggested is exactly what is usually done. This is what we call epsilon greedy exploration. And just to say that at every time step, you either follow the policy with a probability of 1 minus epsilon, where epsilon is a very small value. So most of the time you will follow the policy, but with a probability of epsilon, small, you will act randomly. Yeah?
So it doesn't depend on how many things we know and how many things we don't know?
Not yet, not yet, not yet. Okay, and if you do this trick, epsilon greedy will eventually explore the space. Okay, but of course it will keep also doing random moves, which may not be optimal eventually once actually you have visited enough parts of the state space. So then the question is also not how, but when should you always explore? And so this leads exactly to, I suppose, what you had already in mind. Maybe we should just only explore areas for which the goodness or the badness is not yet established. Okay, and then we stop exploring this. So we stop making random moves in these states. Okay, so how to do that formally? So we can define V plus of S to denote an optimistic estimate of the utility of S. Okay, and we can also define N, which is the number of times action A has been taken in S. Okay, so N is a function of a pair of S and A. Okay, and then we can do, so in this case, for value iteration, the update would become V plus at the next, for the next iterate of V plus would be the immediate reward plus the discounted maximum of the expected utility, but actually it's not the expected utility of the next state. It's the value of some f function, which in this case would be an exploration function, which is the function of two parts. The first part is actually the expected value of the next states. Okay, and the second element is the number of times we have taken action A in S. Okay? And so one possible choice, for example, for the exploration function would be V, so the current estimate of the expected value of the next state plus k over n, where n is the number of times we have done this action A in S. Okay, so what we have is a function which increases with the expected value of the next state and then decreases with the number of times we have visited the states. And eventually, for this choice at least, when n becomes large enough, this quantity will vanish to 0, and we would fall back to just v, which is what we want to actually use and target. Okay? If you remember, actually, this is also similar to MCTS, Monte Carlo tree search, where we had also a similar trade-off between exploiting or exploring nodes in the game tree. Okay, so this was the model-based approach. Now, can we actually learn an optimal agent in the model-free case without explicitly instantiating P or trying to estimate P or R? The issue is that, okay, before what we had is that we had temporal difference learning, which we can use to estimate V pi, okay? And we know that an easy way to improve a policy is to do a one-step look ahead. Okay? So one-step look ahead, if you remember. So we can say that pi I plus 1 of S is equal to the arg, the arg max A of yes. S prime. Okay, so in our case, so in the model-free setting, we know that we can evaluate this, okay, using temporal difference learning. That gives us an estimate Vi, okay, for the current policy I, okay, and we know that we could improve this policy using a one-step look-ahead update, in which we say that now the new policy is such that the action that we would take is the action for which the expected value of the next state is the largest. Okay, but to do that, we need this, which we don't have in the model-free setting. Okay, so we can't use this trick to improve the policy in the model-free setting. Okay, what we can do instead is to use the concept of a Q value. So a Q value, okay, maybe let me redefine a V value first, and then I will compare that to a Q value. So the state value Vs of some state S is the expected utility starting in S, okay, and then acting optimally onwards. Okay? So you are having S, you collect some reward, then you assume that you keep acting optimally. Okay, and then the expected value of the sum of expected reward is the V value. Now, what I will call the state action value Q, okay? So Q now is not just a function of S, but also a function of A. So the state action value of not a state, but a Q state, which I will just define as a pair S and A. So a Q state is just one of these chance nodes that we've reached. Okay, I will say that the Q value of a Q state is the expected utility starting in state S, receiving some reward, then doing action A, and then acting optimally. Okay? So the choice of the very first action is imposed by the Q state itself. Okay, but then after this action, you say, even if that action was not necessarily optimal, okay, you will then assume that you are acting optimally. Okay? So because of that, we have that the value of a state is also the value is the largest Q value over all possible actions. Okay? Does that make sense? If you say that a Q value is, you start in a state, then you impose the next action, and then you act optimally, then this relates to the V value, which is to say you arrive in S and then you act optimally. Okay? The only difference are the first action. So if you iterate over all possible actions and then take the largest, according to the V values, then this is how they are related to one another. Okay? So the V value of S is the maximum of the Q values over the Q states S and A. How is this useful? It's useful because now the optimal policy can be re-expressed as a function of the Q value instead of the expected value of the expected V value of the next states. Okay? So we know that the optimal policy is given by the action that maximizes the expected V values. But if we had access to the Q values, okay, we could just iterate over them and then pick the action for which the Q value is the largest. Because we know that then after this first action will be optimal. Okay? And notice that in this equation, we are not using P. Okay, then you will tell me, but how do I obtain the Q value in the first place? But okay, if we have them, okay, you should realize that then we don't need P any longer. Okay, how to obtain P? How to obtain Q? Well, we have actually Bellman equations for the Q values. Okay, so since the V values and the Q values are related in this way, the Q values can also be recursively defined. Okay, so the Q value is the immediate value that you receive because you've started in S. Then you say, okay, the action that you will follow for the first action is A. Okay, so here you don't have a max over A. You just say, I'm picking A. Okay, but you still have a discounted sum of expected rewards. Okay, you don't know the next state at which you will arrive, so you have to iterate over all of them, and you know then that you will be acting optimally, and therefore the expected sum of discounted reward is the V value of the next state itself. Okay? And now if we use this relation, we can replace V by max over Q over the next state S prime and over the next actions A prime. Okay? So here the action A prime are about the second decision, not the first but the second. Okay? Because we assume that then we are acting optimally. So from the second onward, we are acting optimally, so we have to iterate over all possible actions if the only thing we have access to are the Q values. Okay? And so this is nice because as for value iteration, that last equation can be used as an update equation of a fixed point iteration procedure. And actually, the value iteration algorithm we have seen, you can transfer it to compute Q values, to estimate Q values. Okay, just replace the Vs by Q of S and A, and using that equation. However, okay, this is fine, but we can't do that because we still require the transition model, which we don't have. The trick is to say, or to realize that we can actually adapt the temporal difference algorithm to compute the Q values instead of the V values. Okay? So in the model-free setting, where before we used temporal difference learning to learn V, okay, now we'll use it to learn Q. Okay? And we'll use a similar update. So instead of saying V of S is equal to Vs plus alpha, I don't have it there. Vs plus alpha R. Something like this, if I'm not mistaken. So this is the temporal difference update, the TD update, where we are building this estimate, these predictions, which we compare to this target. Okay, and then we improve using this gradient descent over the TD error. The alternative to learn the Q values directly is given by Q learning, in which we'll build estimates of the Q value, okay, which will update iteratively also from transitions, and we'll have the current estimate plus alpha between the prediction, the target. So in this case, the target is the same, okay? But we are not building an estimate of V, but we know that V is related to the Q values. Okay, we know that V is equal to max A over Q. Let me prime Q S prime. Okay, where here we would be using our current estimates of Q minus the current estimate QSA. Yep. Okay, so if you run these updates on the transitions that you observe, you will learn the Q values. And once you have the Q values, you can extract the optimal policy. Well, how? Because the optimal policy at S is to pick the action A for which the Q value is the largest at S. Okay, what you should realize is that with these two lines, we can learn and discover or identify agents that are optimal even if we don't know anything about the environment. You just need these two lines, or rather this single equation. Okay, so we have summarized how to be smart and optimal in any MDP, even unknown, by one single equation. This is Q learning. Okay, so the full algorithm is summarized here. The main part is this equation that we've derived together. If you want the more complete version, well, at every transition, so this is a function that you would call at every transition, every S, R, A, S prime. Okay, you check if the current state is terminal. in which case you store, you use as an estimate for Q in S and then no next action, the reward that you have collected in S. If on the other end you have reached a next state, okay, then you increment the number of times you increment the number of times you have visited this Q state, so this pair S and A. Then you do the Q learning update on the Q value using this single transition. You have the same equation as mine, except for alpha, where here you see that alpha is now a function of the number of times you have visited the states. And for this algorithm to converge properly, you need the learning rate to eventually vanish to 0 as the number of times you visited the Q states increases. Okay? But other than that, it's the same. And then the next transition will be given by some action here, given by the maximization of the exploration function, f, which is now based on the Q value and the number of times you have visited these possible next states. Okay? So does it converge? The answer actually is yes. Q-learning will converge to the optimal policy, even if you act suboptimally. Okay, so this is called off-policy learning. And why are we acting suboptimally? It's because we have this f function through which we are actually not following the same policy. We are, for example, following a random policy. But even in that case, even when we do the learning of policy, so without actually following entirely the policy that we are learning ourselves, we can learn. Okay? There are, of course, assumptions. You have to explore enough. You have to have a learning rate, which must eventually become small enough, but also it should not decrease too quickly, and so on and so forth. But under these assumptions, it will work. Questions? Do you think you could apply this Q-learning algorithm for a third project to learn how to play Pac-Man optimally? If I'm asking the question, maybe there is a trick. So could you apply could you implement these 6 lines of pseudocode to learn how to play Pac-Man? Yeah.
Maybe the Q array would be way too big because you have many states and many actions.
Yeah. So in this algorithm, what we are doing is what you call tabular reinforcement learning, where we maintain a Q table, okay, which is as large as the number of states. Okay, and for each, we have also to compute all combinations of the actions. So this table usually will be huge. And you will, for most interesting problem, you will not be able to instantiate it in the first place. That's a pity. Another problem would be something like this. Let's say we are learning how to play Pac-Man. We are in this scenario in which obviously the current state is very bad because Pac-Man is trapped between the 2 ghosts. Okay. If we do Q-learning and then eventually discover that this part of the state space is quite bad, if then we are in this setting, which is quite different in terms of the states because now Pac-Man is in this other corner, but actually this is a similar situation, Pac-Man will have to rediscover again what to do in that corner. Okay? So even though you may know something about this, you will not know anything about this in naive Q learning, nor actually you will learn about this. You will know anything about this because this state is also different from this one because there is one missing foot dot. So the state is different. You don't know anything about it. You have to rediscover its Q values. So how will you fix this problem of trying to learn more efficiently and trying or not having to instantiate the whole table? Yeah.
Maybe instead of states, you could use some sensors.
Yeah, that's another issue. But you would have the same problem. So but yeah, by the way, reinforcement learning also generalized to partially observable environments in which you don't observe the states, but you only have partial observations. And you can similarly associate Q values to observations and actions. Or rather, histories of observations or belief states that you've computed from the observations. Okay, so how do we fix this problem? So basically, we have a problem where we have as input a state and an action, and we want to produce some output, which is a number, a Q value. And we are building a data set of these pairs, inputs and outputs, as we run the agent.
Will it take many things from the state? Like the place of the dot?
Okay, you could design your state space precisely just to have the right amount of information. But even in Pacman like this, I mean, this dot is not the, I mean, this state and this one, they are not the same because they are different. So they are distinct value. Yeah. Yeah, so you can use instead a model, a machine learning model, like a neural network to learn a mapping between inputs to outputs. And if you do that, then we'll never have to instantiate the Q table itself. We'll approximate it with a function, which can be large also, but usually much smaller than the product of the state and action spaces. Okay. And if we architecture this function quite well, we could also certainly architecture it. It's just that if we learn something in this setting, then we'll also learn something in this setting. Okay? So this is what we'll do now. We'll replace the Q table by a machine learning model. Okay? But for a machine learning model, first what we need are features. Okay? We need to have transformed a state into a vector of numbers, okay, which we call features. But we could assume that we have these features. Okay? We have a bunch of functions fk that goes from state to real numbers, and that will capture some important properties of the states. And so in the case of Pacman, we could design a function which, for example, let's say f0, tells us about the position of Pacman. Then a second function f1, which tells us about the distance of Pacman to the closest ghost. Then a second function about the distance of Pacman to some food, the closest one. And so on and so forth. So you can be creative and describe your states in this way through feature functions. Once you know how to transform a state into a vector of features, okay, then we can build a data set, okay, that goes from states to values, okay, except that in our case, the values will not be directly given. They will be, for example, this or this one. This one. Okay, the outputs that we want to predict. And so, and also you can do that either at the level of states individually, but you could also have features describing Q states, okay, so that are also taking into account the action which was taken in S. Okay? Then what we have is now that, for example, in the case of, let's say we assume a linear model. Okay? So linear model will be simply a weighted sum of the features. Okay? So we'll have weight 1 times feature 1 plus weight 2 times feature 2 and so on and so forth. We'll just mix all these values together by doing a big weighted sum. Okay? And that gives you a number. That will give us a number. Okay? Which we'll interpret as the Q value. Okay? The value of the Q state S and A. Now, instead of directly updating the values themselves, okay, since we are not directly materializing these values in a table, but through an approximation function, a linear model in our case, the only thing we can update is the function, and more specifically the parameters of this function. Okay? So the parameters in this case of a linear model would be the W coefficients. Okay? And so instead of doing this update on Q, now we would be doing an update on the parameters of the function representing the Q table. Okay? And in this case, in the case of a linear model, if we observe a transition S, R, A, S prime, the updates for parameter K would be that the new value of WK is WK plus alpha times the target, R plus gamma times the maximum of the Q values, minus the current estimate of the Q value, okay, as computed through our model, times feature K. How do we obtain this update? So you can view this problem as a regression problem. Okay, we have some function f of x which we want to map to y values. Okay, and this f of x depends on parameters w. Okay, so we are considering in this case, if y is a real value, a regression problem, a supervised learning regression problem, and a possible loss as a function of the parameters for a regression problem could be, for example, the squared error between our target y and our prediction f of x. Okay? Let's assume that x is fixed. What would be the gradient of that loss with respect to w? If you differentiate this with respect to w. Yeah. Yeah. Okay. Now, if we say that f is just a linear model, so weighted sum over the features, and we differentiate with respect to some parameter. Exactly. Okay, and now if we do an update by gradient descent, by gradient descent, we say that WK, like this, is WK minus learning rate in the opposite direction of the gradient. Okay, this is the gradient. We have minus minus plus. Okay, and what is y? In this case, our target y is r plus max a prime okay minus q s fk. Okay, well, this is okay. Okay, so that's the same in the slides. Okay, but you should realize that we are just doing the same Q-update as in Q-learning or tabular Q-learning. Okay, but instead of doing directly on the values, we are doing on the parameters representing these values. Okay. All right. So this was the case of a simple linear model. Of course, you can use a more sophisticated and powerful model. If you say that you swap your linear model with a neural network, then what you obtain is an algorithm known as DQN for deep Q network, where you have now replaced the Q table by a neural network. Okay? And this kind of neural network, you can use them to play almost any game. I mean, simple games, but that will work. Okay? So I will skip the demo, but basically you can, I had before a demo where I was using DQN to play Pac-Man, the same Pac-Man as you were doing in the project, but instead using a neural network trained using Q-learning, and you could have seen that it was working very well, except because reinforcement learning is not very efficient. It takes a whole night of training before starting to do a good job at playing the game. Okay? All right. So now let me finish with a few applications of reinforcement learning. So you can use basically reinforcement learning every time you want to learn a policy. You are dealing with an environment, and then you want to discover a policy to act optimally under this unknown environment. That's something you can always do with reinforcement learning. In this first video, you would have a long explanation about how to use Q-learning and a neural network, taking as input the pixels of this game of Mario Kart in order to actually play Mario Kart, and doing so eventually optimally. And that's it. Everything that we have seen can be used to do that. A few more examples is this case of playing Atari games. So this one I think is quite interesting. So I don't know if some of you are good at this kind of games of flipper. I'm myself very terrible at this game. I would just act randomly and push on the two buttons there. And initially, of course, the agents cannot play very well, and it's certainly just doing random bumps. Most of these actions there are completely useless, because the only useful actions are the ones that correspond to when the ball hits one of the two bumps. So it will take many, many transitions to eventually discover the dynamics between the bumps and the ball. But if you play long enough, which you can do if you are a computer, you will eventually learn that. After 7 hours trainings, so it has learned how to pull exactly the right force to this part of the game, such that by just doing so, it manages to trap the ball there, where every time you pass it through these 2 blocks, you get a bonus. Okay, then it goes out, but then you will see it has also learned to use these bumps and to replace the balls exactly at the right position. And the only thing it uses is this equation. Nowhere you tell the agent what is the game about. The only thing you give it is just a bunch of pixel values, a score, the reward, that's it. And actions that you can do at every time step. Okay, so of course, the goal is not to play games. I mean, not only to play games. So there are many more useful, I would say, applications of reinforcement learning. Many of them are in robotics, where it's difficult to actually design a policy, a program that would control a robot. For even simple tasks, you would think that having a robotic hand and arm which sees an object is an easy task. It's not. You have hundreds, if not thousands, of researchers working on this problem. That's exciting. One approach which was proposed a few years ago and now, of course, has been improved upon is to use Q-learning with a neural network to learn how to see the objects. I'm showing you this one. I know it's obsolete, but I show you this one because it's using exactly Q-learning as you have learned. Of course, there are now much better and more efficient algorithms. But you can do so, for example, to learn how to see the objects that you have not seen before. Of course, if you learn how to see the cup and only learn how to see to grasp a cup, it will be easy. But if you have an environment for which you don't know in advance what are the possible objects, all the positions they can have, and so on, it can be a difficult task. And you see there, okay, it's using Q, this Q function, cross entropy, whatever, but it's just gradient descent over the Q states, over the Q-learning error, and so on. And here, everything is done in real life. Okay, so we don't simulate anything. They don't simulate anything. They have several of these robots in parallel that are just there to run the policy in real conditions and to collect transitions from which to learn. So in this problem, you may notice that actually it does not look like a hand. It's just what we call a gripper. So you have 2 opposite terms that just close. So this is very easy to actually learn how to control. If you add instead a whole robotic hand, then it becomes much more difficult to learn how to use. Another example I want to show you is this one. So this is about controlling drones to do racing and to do. So you may know that there are actually races where humans are playing the virtual pilots of these drones and try to go as fast as possible. And so you can do the same with reinforcement learning. You can learn how to control these drones. The difficulty here is that it's moving very, very fast. Okay, so you have to take actions very, very quickly. The state is only known partially. You may have, for example, a camera equipped with on the drone, which is looking at the scenes, and then you have to make sense of that to take actions. What is also interesting there in this video is that it's mixing reinforcement learning with Kalman filter, which we have seen, to actually try to estimate the states, and then from this estimate of the states to decide the action.
Drone racing is a thrilling and fast-paced sport in which pilots control small drones using a live video feed from the drone's camera. The objective is to navigate the predefined course and pass through all of the gates in the correct sequence, faster than any of the other competitors. It is a test of skill, strategy, and quick thinking, as the pilots must maneuver their drones through the challenging racetrack at high speeds. In this work, we present Swift, the first autonomous system to achieve champion-level performance in drone racing. Swift won multiple races against the champions of 3 different drone racing leagues and achieved the fastest recorded race time. All of this while only relying on an onboard computer, a single camera, and an inertial sensor. Swift uses visual inertial odometry, also known as VIO, to estimate its own position, velocity, and orientation. While such an approach produces accurate estimates when operating in near hover conditions, these estimates substantially degrade at the speeds encountered during drone racing, as shown in green. To improve the estimation quality in such agile regimes, Swift complements the estimate from the VIO pipeline with a learning-based detection system that segments racing gates in the images captured by the onboard camera.
So basically,
Given
there is
the
a small
position of
CNN.
the gate in the world frame, Swift uses the PNP algorithm to triangulate its location. The animation shows one or more gates being detected during a flight. Swift uses a Kalman filter to combine the estimates from the VIO pipeline with the pose estimate obtained from the detected gates. The uncertainty of the estimate of the PNP algorithm decreases quadratically with the distance towards a detected gate. As a result, the variance of the Kalman filter posterior also decreases when approaching a gate. Racing a drone at high speeds through a complex track requires quick and precise control actions. This is especially challenging when using a camera for state estimation, which produces noisy estimates of the drone's state. To overcome this challenge, Swift uses a learning-based control policy that directly maps noisy state estimates to control commands, allowing for rapid and accurate steering of the drone. The control policy is represented by a neural network and is trained via deep reinforcement learning in simulation. During the training process, the control policy explores the environment using 100 agents in parallel and finds faster and faster paths through the track layout. The entire training process takes less than 1 hour on a normal desktop workstation. To prepare the control policy for the noisy and imperfect state estimates available on the real system, Swift uses flight data collected in the real world to identify residual models for perception and dynamics. These residual models capture effects that are difficult to model in simulation, such as the degradation of the vision-based estimator or turbulent aerodynamic effects. Swift uses this augmented simulation to fine-tune the control policy for real-world deployment. This results in a highly competitive policy that can cope with the uncertainty of the real system. We benchmarked the performance of Swift against some of the best human pilots in the world. Swift raced against Alex Vanover, the 2019 world champion of the Drone Racing League. Thomas Bidmata, the 2-time multi-GP International Open World Cup champion. And Marvin Schoppler, the 3-time Swiss national champion. When comparing the trajectories flown by the humans and Swift, we notice that the autonomous system is more consistent across laps and is able to take tighter turns. This gives it a decisive advantage in a race. Swift won multiple races against each of the human champions and achieved the fastest recorded race time. This marks the first time that an autonomous mobile robot has achieved world champion level performance in a real-world competitive sport.
Okay, so this is mixing many of the components we have seen together. So to be fully honest, it's not directly using Q-learning, this one. It's directly using a neural network to implement Pi, okay? But which you would learn with algorithms that look like Q-learning, I mean, to some extent. But the goal is the same, to find an optimal policy. What is also different is that we don't know S, we just have noisy observations, and this observation can be really, really noisy because of the speed. And so what they were doing instead is to build an estimate, a belief state, using Kalman filter. Then once you have this, you can learn in simulation how to solve this task, okay, in order to find something which is almost the optimal policy, okay? But actually, because we can't simulate the real world very well, okay, then we need to account for many. So there will be a gap, about the policy that you learn in simulation and how good it will be in the real world because of the misspecification of the simulator. So you can do some of the tricks, but these are just things that you know. Okay? All right. Okay, so to summarize, today and last week we have covered Markov decision process. We can solve them if we know them using value iteration, policy iteration. If we don't know them, there are two ways to solve the problem. Either you build a model first of the MDP, then you solve it as a regular MDP, or you just use a model-free approach in which you would directly try to estimate the V-values or the Q-values without ever explicitly building a transition model or a reward function. Okay? And the main algorithm that we have seen about reinforcement learning is the Q-learning algorithm. That's really the main one, together with temporal difference learning that you should remember about reinforcement learning. Okay? So with this, I can almost conclude the course. So at the very beginning, I've told you that my mission was that by the end of this course, you will have built autonomous agents. I think we can agree that's the case. That efficiently make decisions. They make decisions. Efficiency is maybe not achieved yet, but at least they make decisions. In fully informed, meaning when the environment is known. Okay, we know to do that. But also in partially observable and adversarial settings. Partially observables, we know how to account for everything we know we don't know by building a belief state about the actual state and then basing our decisions on the belief states. And adversarial settings when there are other agents in the game or in the environment. And then your agents will be able to draw inferences, so to take actions or to simulate what would happen if. In uncertain, okay, we know how to do that, and unknown environment, we also know how to learn about them using machine learning, together maybe with reinforcement learning approaches, and then to optimize actions for arbitrary reward structures. Okay, so hopefully now, or maybe only later in January, you understand all these words, and you agree with me that we can do that, or at least now we have the beginning of an understanding of how to do that. Okay? All right. So I will just show you one more very short deck of slides, and then that will be it for today. Let me just... Okay, so this is the very last lecture today. And so I just wanted to summarize very, very quickly what we have seen together. So I know that we have covered quite many things, but that's really the philosophy of the course is to give you a broad overview of everything which we can define as AI. So we have started by a generic introduction about AI and thinking about what it means to be intelligent or artificially intelligent. Then we have started defining blueprints about how to actually implement agents in computers. From there onwards, we have seen how to solve problems using search algorithms, and then how to solve problems in which maybe we were faced with adversaries. So that was the topic covered in lecture 2 and 3. But then quickly we realized that, okay, if we only have that, we can't go very far because most of the real world is uncertain. We don't know about many things. We have to take into account all the uncertainty that we may have about outcomes, about our decisions, and about many other things. And so for this reason, a good part of the course is dedicated and was dedicated to how to first properly formalize uncertainty using probability theory, then how to use this framework for inference, so to reason either over a fixed scenario or a fixed environment, or even also to an environment which was evolving through time. We have also built upon this framework to define machine learning, supervised learning problem mostly, which I define as just trying to estimate a conditional probability distribution, but using very, very powerful function below, like neural networks. And so this 7 lecture is really, really important when it comes to AI. Everything related to AI is mostly about neural networks. And so what you will keep learning, certainly about AI, will be mostly now focused on the learning aspects. Then we have seen how to combine all these things in order to make decisions and eventually to also learn in environment and while still trying to be optimal. So remember that all these topics are also covered in the textbook, okay? So not only with the slides, and I think you will find most of the materials there, but if you want longer explanations, you can check each one of those chapters in the textbook. You will also find similar materials as what I've presented in the course. If you are interested by, if you have become interested by AI, if not, then that's it, fine. But if you have become interested in the topic, this is only the first course of a long series of topics that we offer, of courses that we offer in the various programs of the university. So all of these courses are available in the master programs. So you will find an introduction to machine learning. If you go, for example, in most of the master in engineering, at least, you can follow an introduction to machine learning. It's either mandatory or optional, but if you go, for example, in data science or computer science, this will be part of the common core of the courses. You may also be interested in data science, and so what we've covered in this class will be useful also later. If you are more interested by the learning aspects, there is also a full course about deep learning, so just about neural networks, which I'm giving to the master students. You may also be interested in advanced machine learning, so if you want to go one step further than that, you will also be able to do that. So in this course, it's closer to research. So with the students there, we present and read papers together, scientific papers, then which we discuss and so on. You have also this course, which actually has been renamed now. It's reinforcement learning given by Damien. You also have a few courses which are not directly about AI or deep learning, but which do use this technology or this concept to do things. So Introduction to Intelligent Robotics is one of them. It's mostly a course about robotics, but to do anything useful, you will need a concept from AI, like neural networks. And similarly for computer vision, these days, when it comes to research in computer vision, everything is based on neural networks. And so also a good part of this course is about that. There are plenty of other courses. This one was created last year. It's about machine learning in space science. So all applications of machine learning to space science from Earth observations to astronomy and cosmology. If some of you are later interested by internships, feel free to contact me. If you are looking for a summer job, we can always find interesting projects for you to work on. If later you want to do a master thesis, also feel free to contact me. And if some of you are even considering PhD thesis, you can also come to me and we can discuss about opportunities. My last slides will be this one. I mean, there is one more, but about what I want to say. Really, what I want you to have learned during this course is that AI is much more than ChatGPT and also Pacman, even though we've used Pacman a lot, but mostly it's much more than ChatGPT. Everything that you hear these days or read in the news is mostly about ChatGPT or chatbots, LLMs. It has become a huge part of the field because this is the most direct thing that the larger public sees about AI, and it's the easiest certainly to interact with. But I hope that you will have now realized that this is also just a small part, which is getting bigger, but still a small part of AI. Okay, and what I really want you to also remember is that I don't really care myself about Pacman and trying to play Pacman very well. And I suppose that's the case also for you eventually, even though that's funny, interesting, and we learn concepts, but this was just a way to teach you all these concepts. What really you should remember is that many of these techniques, many of this way of framing a problem and then trying to solve it, are things that you can reuse in plenty of other contexts. So there are plenty of really nice applications, for example, in science, in engineering, or to solve societal problems, where you will be able to reuse many of these things that we have seen together. Okay? So if you want to build, I don't know, the next generation of aircraft, of cars, or robots, certainly you will need AIs to do that. Okay? If you want to make the next app to change the world, certainly it will be based on AI these days. If you want to work on, I don't know, the next generation of medical devices, of course, you need to know a lot about medical stuff, but it won't be enough these days. Many of the things, the discoveries now are also helped through AI. If you want to analyze large amounts of genomic data, process images, everything is based on AI. If you want to try to understand things we don't know yet about, like how the brain works, what is the universe made of, yeah, I'm sorry, but you will have to use AI if you want to answer these questions. The same if you want to discover new things, new drugs, new materials. Everything now these days is driven by this technology. Okay? So by that, I mean that as future engineers that you will be or scientists, I believe that AI will offer you many opportunities to address many of the most interesting challenges that we have and that we are facing today. Okay, with that will be my final word. Thank you. Okay. We can do the break now. There is still an exercise session, I'm sorry. And so we'll do the break. I will also start maybe with a few words about the exams, what I expect, what kind of exercises you should expect, and so on. So we resume in 10 minutes.